Okay, so I'm going to go ahead and get started. So for this portion of the talk, this is where it really will pay off if you have a computer in front of you, because I really want to step through the source code and look at specific things there to just start building some familiarity with the way that these things work. So if you can take your web browser, and so I know everybody uses different IDEs, right? So to look through the code, what we're going to do is just step through the code as it's viewed on GitHub, because I feel like that's a common denominator for everybody. So if you go to su2.stanford.edu right now, and scroll down just a little bit, you'll find a link that says High-Level Source Code Overview. And so the page that this links to, we're going to put in a more permanent location, but for now, this will at least get you there and get you started. Right, so in lieu of any kind of PowerPoint presentation, I've just put this web page up, and what's nice about doing it this way is that every link on this page will actually take you directly to a location in the source code on GitHub. So you can look through this and you can see exactly what you can find the location in the code of exactly what you're looking for. So the goal of this talk is to familiarize the new SU2 user with the most important data structures and the high-level patterns that are in the code. And so if you look in the main the SU2 home directory, you'll find that there are quite a few subdirectories and there's quite a few source files. But for the sake of focusing this discussion, we're only talking about the CFD solver, and the directories that will be important are just the ones that are listed here. So the SU2 CFD subdirectory, there's the source and include, and in this little table I've just told you what's in there, so it's pretty straightforward. The source files are the .cpp files, and the include files are the headers and also the .inl inline files. And so in addition to CFD, there's another subdirectory called common, which includes things that are related to config, geometry, and linear solvers, things that can be used in really broad applications. And it also has a source and include directory. And just to be very specific about it, the different file types that you'll find that make up the source code. .hpp, the only things that are in there are declarations, which is the C++ terminology. And if you click the hyperlink that I've included here for an example, it'll take you to the declaration for the C Euler solver. And so this is in one of our header files in the solver structure.hpp. And you see here the declaration of a class. So this doesn't have any functional source code, but it tells the compiler all of the things that it should expect in this class. And there are quite a few classes, as you'll find, and they all have declarations in these header files. The inline files are function definitions, so they do include some source code, but these are strictly things that take no more than 3 lines, right? So I'll just mention in case it's unfamiliar to some people, if you have an inline function in C++ and you call it somewhere in the code, when the compiler arrives at that location, it'll itself replace that line with the lines of the inline function. So you wouldn't normally do this for anything more than 10 lines of code, and really our typical inline functions look something like this. So here's an inline double get velocity inf. It has one input, which dimension you want, and the only bit of code that's actually executed is this line here. It simply returns this member. And so as Brendan was mentioning previously, all of the variables that are inside classes are declared as private. This is for what's called encapsulation. And if you need to access these data members, then the way to do it is through these getter and setter classes. Or methods, rather. Getter and setter methods. Okay. And so with that much under our belt, I just want to point you to the code entry point. So if you go to su2cfd.cpp, this is where the code starts. This is where our main routine is. And if we scroll just past this licensing information that tells you that it's open source. Oh, wow, it's very difficult to see. Okay, does that help?
This key is perfect. It looks okay. Everybody has a laptop, so we can probably.
Yeah, everybody.
Don't worry about that.
Okay. 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 So if you scroll just past the licensing information, you find this first bit where it lists the pseudocode, and this is definitely worth looking at. It just tells you what's going on in this file. The first block of it is various kinds of initialization in the order that they happen. And then there's this block here, which is the solver itself. So you have a loop over this variable external iteration. yeah, next iter is the global iteration number. And then we evaluate our residuals and we check to make sure it's fine. And then at the end, there's just some cleanup that happens. And just below that is int main, and this is where the program starts. Okay, and so we'll come back to this when we step through the code. The last thing that I'll do in this talk, just to give you a heads up for what's coming, is we'll step through the code as if we are the computer and go through one step of the solver. There's a question from the audience?
Yeah, like in the code, there's the zone. The zones is kind of set to 1. Two questions. One, do you expect that to change anytime soon? So you could have multiple zones?
Yeah, so do you want to answer?
Yeah, so right now you'll see zones in there. What those are is basically those mark special regions inside of the mesh. We basically want to separate certain pieces of meshes into multiple zones because sometimes they may be moving relative to each other, or you're solving different equations in the zones.
Is it like for coupling?
Or you're using them, yeah, or you're using them to couple at a boundary. We use them, for instance, for the supersonics work. We have a special near field condition where we extract signatures and these types of things. So that's a feature that we've used for a number of projects that we haven't developed fully in the sense that you could do a lot more with it. We're starting to talk about expanding that and doing more complete sliding mesh interfaces and these types of things with it. So I think you will see that grow a little bit.
And this is also related with my statement before. So we know that there is a group in the Technical University of Delft, and there is another group in Politecnico di Milano that are working on that kind of the code. So if you want to work on that, it's much better if you contact us and we will point to the person that is developing those capabilities.
Another idea is that, sliding mesh interfaces, overset meshes, these types of things where you have just multiple zones within the file. You want to have independent regions in the mesh that you want to treat differently in some way. So that's really what those are for. So. And we've also used it for time spectral method as well. So if you have problems with inherent time periodicity, you can have multiple solvers launched at one time, and we put those in the zones. And you can have, say,
so the
10.
feature's functional, it's just not, it's not turned up.
Well, it's there for the most part. It's just you only need it for certain applications. So.
Okay, great question. Thanks. Okay, so the next thing I want to talk about is to just describe some of these data structures. And so we were just looking at the main routine. And if you scroll down not too far at all, you'll find this block that defines quite a few pointers with quite a few indexes. So let's just talk very quickly about what these are. So the primary data structures have several indexes. So you might find one that looks like this. So there's a C numerics class, and you see that there's 1, 2, 3, 4, 5 stars defining the dimension of this data structure. So let me just talk about it rather than try to give a very global definition. The number of indexes that you need if you want to access information in this is going to be n-1, if n is the number of stars. So I've chosen the example here. This is the most. There's 5 stars here. You'll need 4 indexes to get information out of this. So if you wanted to access numerics container and call any method that it refers to, the way you would do it is with 1, 2, 3, 4 indexes, and then this final notation tells you that it's after you've dereferenced it 4 times, you still have a pointer, so you point to some method that is contained in that class, right? So for the every one of these data structures, you can use that pattern. So what are these indexes? What are these indexes referring to? And in different places, there's different names, and it's included in the comments also, so I've just tried to give a general sense of what these indexes might be. The zones, or if maybe it says n zones or I zone in some places if it's inside a loop. The zones index the zones in the mesh, and this is the conversation that we were just having. So that's used sometimes for multiphysics and a few other applications. Then the second index might be mesh, or maybe number multi-grid grids. And this is the index for each multi-grid level. So the finest mesh will have an index of 0, and then the next coarser mesh will be 1, and so on in that manner for however many meshes you have. The next one is number of EQ systems, or ISOL, or equation. And so this refers to the different types of equation that can be solved. And so this, for this index, you wouldn't typically put an explicit integer. Like nowhere in the code would you say, okay, in this index I want equation system 2. That's not really the pattern. Instead, you would use you'd use a variable that's a constant integer. For instance, flow sol would refer to the equation system that is the mean flow equations. Whereas if you use the index turbsol, now you're referring to the equation system associated with the turbulence model. And if you want to see the list of what are your options for this, I've included the link to the source code itself where these things are defined. And you can see it right here. So all of these right here are the various equation systems that are implemented and how you might want to refer to them. And then finally, for the numerics container, there's the last index, which is the equation term, or I term. And so this refers to a term of the equation system that you're working on. So if you're working on, for instance, the viscous term, you might use visc term or conv bound term. And once again, this is not a place where you would use an explicit index. Instead, you would use one from this list. And that is located right down here. So these are convective term, viscous term, et cetera, et cetera. Okay, and stop me at any point if there are any questions or if anything is unclear.
Maybe we can just a little bit. So the idea here is that we are developing a multi-physics code, so there is a very strong logic between this kind of decisions. If you want to develop a multi-physics, you are going to choose different numerical methods. So the first choice that you are going to do is this numerical method is going to be applied on the viscous term, on the convective term, on the boundary. This is one of the index. Then you will choose what is the equation that you want to solve, because this is multi-physics. So maybe you want to apply that numerical method for the mu flow equation, or the turbulence model, or the heat equation, or the fluid or the FEA equation, and so on. This is the second index. Then we are always working with multi-gate structure. So maybe you want to apply that method only to the finest gate, because in the coarse gate you want to apply another numerical scheme. That's the reason you have the multi-gate, the index of the gate. And finally, the zones. Maybe you are dealing with a multi-zone problem. So depending on the zone, you will apply a different numerical scheme. So there is a logic behind all this kind of decisions. And it has been optimized during a lot of years. So that's one of the main advantages of SU2. You want to really implement something really complicated in different zones, using different gates, different equations, and different terms in their equations.
In the multi-physics, you also, I've seen cases where you've had, using modules, in Python, right? So how would you decompose, where you would suggest focusing on zones for your different equation models, and then using it via the modules?
Everything, I think, depends on the kind of coupling that you have in the different system that you want to solve. If you want to do something that is segregated, maybe Python is a good strategy. If you want a fully coupled multi-physics problem, then you need to go to the C++ structure and guarantee that everything is implemented in a way that is going to converge. So it depends on the problems. Depending on if you are dealing with a strong or a weak link between the different species, different equation of your problem. But my recommendation is to start always with the C++ code.
There's a really good question online that I want to bring back up. It might involve Brendan's presentation a little bit too. So Mark asks us, who has the ultimate say as to what goes in the code? Are there checks in place? I'd like a stable version to work on and not have to rerun everything constantly to make sure. So this is a great question. So I'll start it off by saying this is exactly why we moved to this master develop branch scenario, and I'll let Brendan say a little bit more about that, but that's a fantastic question.
So as Tom just said, if you want a stable version to work off with, master is where that is. And I don't know if you remember, but when I actually forked the code, all of those branches were forked, not just one of them. So you can sort of switch between branches if you want. So what some of us do, for example, is we'll make changes on develop, but like maybe our changes are complete or whatever, then we can switch to a branch that we know is working and then run from that while we're in the middle of other changes. And that's one of the great things about Git, is you can kind of bounce around. So, and if you don't want to make any changes at all, you just want to run SU squared. Well, if you clone the repository to your local machine, like nothing can automatically change code on your local machine. So you're sort of in control as to when that happens next. So now the other question was like, who decides? And essentially, it's I mean, there's no sort of official voting procedure, but there's kind of a couple of main caretakers, namely Francisco and Tom, who are the main caretakers of SU2, and then there are some core members of the development team that have been working with SU2 for a couple of years. And it's some sort of a discussion-based process where we decide what's good to add and what's not good to add. And sort of the more you're active in pushing changes to the code, the more you sort of demonstrate that you know what the overall vision is, the more you'll be able to be in that decision-making team as well. And that's also why we would like people to discuss changes first, because we don't want people to spend hours and hours of work assuming that we're just going to accept the changes and then find out that it's not within the right vision of the team. So if you want to make changes for your own personal benefit, you can always do what you want. But if you want them to push back up, you really should have a discussion with us to make sure that we're okay with it being added and then going. So for example, if your change was going to be, we're going to delete the mean flow solver and replace it all with a lattice Boltzmann, like that's not going to happen. So before you do that and try to push it up, you should get a confirmation from us that that's not going to happen. So.
Say something about regression.
Yeah, that's where I was going. So then the last thing I want to say about this is we do have regression tests that are running on the branches, the repository that you see in GitHub. So it's always being tested. We have a set of, I don't know, let's say 20 or so of the cases that are the most well-known types of validation cases, some of which I showed yesterday. So we're always monitoring that. And the idea is now that the develop branch is going to be tested all the time, and we are only going to push stable releases to the master branch. So when you pull down the master, you can trust that that version is working. It's working with all of our regression tests, and it's up to snuff. So.
Do you guys publish those results?
The regression tests themselves, I guess we.
So mostly. So
we can.
Yeah. So one of the other repositories in SU2 code is a test cases repository, and that includes the config files and many of the meshes, but you can't push all of it to GitHub because the whole set of data is too large for GitHub. So. So.
The team gets errors if something happens, I guess.
Yeah, if the answers are different than they should, yeah. If you join the development list, you can get those. And if the answers are what they should be, it doesn't say anything. And if something broke, then we all get an email that says the regression script has failed. These are what failed, and that kind of thing.
So you can't see this.
But there's also the SU2 papers that have validation. Right.
Yeah. So there's also
modifying a version that was published. The new version is different than the version that was running that. Yeah.
Well, and so many of those validation cases that you see in the papers are, in fact, the exact same ones that are in the regression tests. So, like the turbulent NACA 012 and the turbulent flat plate, those are in the regression tests. And if those numbers change, you get an error and you have to go fix it. So, while the code itself is changing, many of the answers that come out of the code are not.
But yeah, we are actively monitoring.
Yeah, we know that that's critical for the industry, so we work a lot in the validation to be sure that we maintain the same standard that we started. Maybe the last comment, we have one major release in SciTech every year, and then intermediate SciTech in January, and then we have another intermediate release in the aviation conference in June, July.
Yeah, in June.
So those are the critical dates for us.
Okay. Okay, no, that's a very good detail. It's very
that was
important.
an informal.
Is it,
there are more questions,
on
but let's let you finish up, and then we'll cover some questions.
Okay, great. So the next thing I wanted to address is where is the data stored? I think that's just a question that you want to know the answer to before we get started. And so this is the answer. There's a CSolver class, and inside that CSolver class there's an array, and that array is called node. And every element of node is a pointer to something that inherits from C variable. And this is where...
Use your laptop because there is not clear, but if the laptop is perfect.
Okay. Maybe I'll just turn the projector off. So the C variable node, the C variable class is the container that holds all of your data. This means solution values. This means things like laminar viscosity. This also means things like eddy viscosity, turbulent variables, gradients. Everything is inside there. And so this is just something that's worth familiarizing yourself if you plan on using the code. And I've I've included a link right here that'll take you to the parent C variable class. Now, you almost never will have an instance of the C variable class. It's intended to be a parent to something you'll inherit from it with your own type. But if, for instance, if you're solving the Euler equations, you'll have a class called C Euler variable, which implements all of these and potentially more things. And as you look down, you can see that there's really a lot of data that you might be interested in having at every grid point. Now, like I said, this node array is a member of a C solver class, and it interacts with the numerics class and also this C syssolve class to do the spatial and time integration, respectively. Okay, and I'll just move a little bit quickly now. I have a short list here of some common patterns that are used throughout the code, and these are things that you just will need to know if you're trying to implement something. Getting and setting, we've talked about a bit now. Looping over edges, if you click the link, it just takes you to an example of where you do it, but for whatever algorithm you have, you may wish to loop over all of the edges inside your mesh. And it's very simple to do so, and in general, when you want to do it, find another place in the code where it's done, copy that, and use it as your starting template. So here is an instance in solver direct mean where we loop over all of the edges. If you just give it a second, it's going to take you to the exact line number. Or maybe not. Well, shortly below, this, I guess the link changed. Here we have a loop over all of the edges. Similarly, in the source term, we loop over all of the vertices, which is another thing that you might want to do. And sometimes you might want to access a variable in one equation system that's in another equation system. And I invite you to click through these links, but actually I want to move on to the next part, which is this program call graph. So what I've done here is I've assumed that we're going to be, like, let's pretend that we're the computer stepping through the code. Starting at the beginning, what would we step through to do one iteration of an Euler solve, or actually a mean flow solve? And it's not just Euler because I did include the viscous term, but I've also included a source term just to demonstrate that portion of it as well. So just some decisions were made, but they're for the purpose of illustrating all of the parts. And so I'll describe this quickly, but if there's any time, I really invite you to kind of click through it and see how each of the pieces are implemented. This is what's called an image map in HTML. So any one of these links, if you click on it, will take you to GitHub, and you can see the location in the code where that portion is implemented. So I'll talk through this quickly, and then I'll definitely open up for questions too. We have just a few minutes left. We start at main. That's a very good place to start. And if we're going to be solving the mean flow, we'll step into a routine called mean flow iteration. And this is also a top-level routine, by which I mean it's not inside any other class. It's a top level. Mean flow iteration will call a method that's inside the C multigrid integration class. And this class, the way I've represented it here, this class C multigrid integration is a child class of the C integration parent. So I'm just trying to explain also how this diagram works. So multigrid iteration calls multigrid cycle. Now, if you're familiar with the multigrid algorithm, the first thing you know about multigrid algorithm is that it's a recursive algorithm. So if you want to see how multigrid works, you want to first find that recursion point. Well, multigrid cycle is the routine that calls itself. So that's where the algorithm is recursive. Now, strictly speaking, all our explicit time stepping and everything else are the smoothing operations for the multigrid solver. So I haven't talked about that theory very much, but from multigrid cycle, you have pre and post smoothing, and those operations are the time integration and the time integration and the space integration. So let's start with space integration. We have your residual for your upwind, source, and viscous terms. And for each of those, you'll be making calls to our solver that are methods within our solver class. And then similarly, there are boundary conditions that you want to deal with. Now, all of these spatial terms, that's these 5 right here, will take data and send it to a numerics class. Now, the thing about a numerics class, the numerics class doesn't store any data, and it really is, it's not a class that's intelligent about the larger problem that you're solving. The numerics classes only contain the information that they need to compute a particular spatial residual. So what the solver class will do is it will take, it has some numerics class, such as, say, the row scheme, and it knows what information the row scheme needs. So the row scheme will probably need the data at point I, solution at point I, solution at point J, Potentially other things, laminar viscosity for viscous terms, eddy viscosity similarly, and for source terms it could be all kinds of information. So the solver class will give that data to a numerics class. The numerics class will operate it and return a residual. So that is the way that the spatial terms work. And then when we come back, we'll bounce all the way back to here, and then we need to do the time integration. So for illustration, the time integration that I'm showing is implicit Euler. Explicit is a lot easier, so this is the interesting one. Implicit Euler will move to the CSys solve class, call it solve routine, and the solve routine will call some particular linear solver. As an illustration here, I've chosen FGM reds. So that leaves 5 minutes left in this time block, and I guess we'll make this chart available if you want to click through and use it as a resource. Hopefully, if there's some particular thing you want to implement, you can find the place where it's already implemented, click to there, and take a look at what's already done. And let me just open it up to questions. Yeah.
A comment. So if you take a look at the numeric class, this is probably one of the nicer examples of the combination of applied mathematician and engineer. So when we started the development of this code, there were applied mathematicians and engineers. The engineers wanted to really simulate a complete aircraft, and the applied mathematicians, they want to try their new numerical scheme without the complexity of this kind of huge code to solve complex engineering problems. The agreement was how to deal with the numerical class. The numerical class is a class in which you can implement very easily any numerical scheme, and the only thing that you need are the two ends of your edge where you are going to compute fluxes. Once you have that, you will plug in that into the main structure, and you will be able to use your experimental numerical scheme in a complex configuration. So this is somehow the trade between the engineering and the applied mathematicians' point of view of developing CFD codes.
So I want to repeat what Francisco just said for the first year CFD student, which is to say that in your first year class, you'll probably have to solve a shock tube problem, and you'll probably use 4 or 5 different schemes, and you might walk away from that thinking, I have no idea what this has to do with an actual CFD solver. Well, in SU2, if you just take whatever scheme you implemented there and make it as a numerics class, you now have that scheme available to you in the context of a full 3-dimensional solver. So I know that there were some questions online.
Yeah, there are a couple. So let's go back to zones real quick. We have a question from Payam who asks, is it possible to unify all of the zones in order to run a simulation with SU2 and get the results with all the zones that have been specified in the mesh file? So I'll go ahead and start the answer to this one. We have done this a little bit in the past. Right now, I think the capabilities are a little bit limited in the zone framework because we've only used it for a few applications. But that being said, again, we do have some folks who are working with us on multi-zone capabilities at Delft. I expect this capability to increase in the next 6 months or so, so keep your eyes peeled for that. And if you're interested in working on multi-zone type calculations, just let us know. We'd be happy to show you kind of the ropes of the zones and how to work with the output routines.
Yeah, probably one of the critical parts of the zone is how to implement the matching between the boundaries that are shared by the different zones. And we have quite a bit of experience on that.
Okay, there's another question. How do we add new shape parameterizations like B-spline? And that's from Jonathan.
You want to take that? I think Tom.
So we have a section of the code where we have most of our design variables, and you'll find that inside of surfacemovement.cpp, I believe, is where we have all of our different design variable parameterizations. Right now in 2D, we have a lot of things such as Hicks-Henny bumps, different types of bump functions. We have the freeform deformation variables that you saw Francisco discuss yesterday. So inside of there, you're going to find a bunch of routines where you can actually move the surface based on a particular parameterization of your choosing. And so inside of there, you could go ahead and add a new subroutine that can move variables or move the surfaces of your mesh as you so please. And you'll also need to hook that up with the config options in order to specify that. So,
this is a perfect question for the CFD online forum or for this week in SU2. So every Wednesday at 10 Pacific time, we answer those kind of questions live.
okay. So we have another question, I think, Aniket, this one's good for you.
Sure.
Somebody is curious where exactly the main loop is held where you're computing these fluxes. So basically, I think they're asking, well, what is the upwind residual? Like, where do you loop over the cells and faces
Sure. Okay. So
to compute convective schemes?
yeah, if the very specific question is where do you loop over the cells and faces, the answer is inside this solver class. For instance, if it's the convective scheme you're interested in, you can click right here on upwind residual. And what you'll find in this routine is a loop over the edges. So scroll down just a little bit, and it's the very beginning. So this is the loop over all of the edges in the geometry, and then I think that's pretty much the answer to your question. Now, to go from inside this loop, you'll be calling the numerics class. That's what this call graph is showing. So upwind residual, and you can trace this thing down to where it actually calls the row scheme. And the calling of the row scheme, it happens in, well, after all of the setup is done, we want to compute, it'll be numerics compute residual. And it's right here. So this is the actual line where it jumps into the numerics class and performs the operations that are the row scheme. Everything prior to this is just the setup before it does that. And everything after this is also important. Let me mention this as long as this is up. Because we're not only computing the residuals from the row scheme, we're also computing the Jacobian, and that's important for the time update. So the Jacobian for both points I and j come out of this, and here we give them to the linear system for the solve that's going to happen later on. Okay, anything else?
Yeah, we can show the space integration that is very useful, the space integration in subroutine.
Okay.
Yeah, that's in integration structure.
I know where it is. It's right here.
Very handy.
Got it.
Okay, so here's the space integration routine. The first thing we'll do is compute the, well, it says inviscid residuals here, but really convective residuals. And so depending on whether you're using a space-centered or space upwind scheme, it has a different call. But so just to place ourselves in context again, the space integration routine is in the C integration class. The routines that it calls will be in a C solver class. So that's why it's, you know, we're accessing the pointers in the solver container and we're calling their methods. Okay, so here's the convective residuals. Here's the viscous residuals. Here's the source term residuals. And then here's dual time for unsteady, actuator disk. There are a number of additional things here. And then the boundary conditions are separated into two as well. They're what are called weak boundary conditions. This is a nice bit of vocabulary to have. A weak boundary condition is one that once this solution is converged, that boundary condition will be enforced. So for instance, if you had a weak no-slip condition, at any iteration prior to convergence, you might have some velocity at that point, but at the converged solution, you should have the no-slip condition satisfied. So that's called a weak boundary condition compared to a strong boundary condition, which are present below, and those are the ones that are enforced at every single iteration. And that's it. Okay.
Yeah, I think we should move on there. We have a few more questions online, but yeah, we'll save some of the specific developer questions for after Santiago gets his talk. So one more minute while we set up here.
I'm just going to send you